Now let's do it with relativity. So now let's take P total from S to S prime with special relativity. What that means is when we convert from S to S prime, when we change the velocity, right, because momentum depends on velocity, when we change that U, we have to use the relativistic velocity transform. So let me show you where it shows up. So say we were going to write P, the total momentum in the prime frame. What does that equal to? Well, you know you have to sum all the masses, their mass matters, mi, and then it would just be ui, or ui prime. So what is ui prime if we get it from the speed u in the original unprimed frame, say the lab frame? Before, it was just ui minus v. But now, for a relativistic speed, we have to put the thing in the bottom. 1 minus ui v over c squared. That's the relativistic velocity transform that I ran out of time to show you in class. And I'm probably going to make another video about it. So I officially told you, you can look up in the book. That's how you get from one frame to another. If it's the motion along the direction of u, then y and c were a different formula. Okay. So you say, okay, let's use that. I mean, it's still going to conserve momentum, right? Let's check here. Let's see. So we use that formula. I mean, surely, like, even though it's different math, it's still going to... P, let's see, total prime. Let's do that previous problem we did, but this time use that, since it was relativistic velocities anyway. So the P prime, it was 4 times 0. That left mass wasn't moving because we're moving along with it. So relativity doesn't affect that, it's still 0. Minus 3. Now this speed will be different. It's not just u minus v. It's got other effects. It's got the relativistic part in it. So it's 0.946c if you go do the numbers. Okay. So that means our momentum minus 2.84c. Different value, but we don't panic yet. Okay. Maybe it'll still be conserved. Who knows? Let's see. So then we go to the final. This was the initial, and this was the final P total prime. And what is that going to be? So now the thing is moving. Oh my God, again, I can't read it. 4 times minus 0.882c minus plus 3 times 0.385c. Just plugging in the numbers from the previous problem. And just accept with this different transform. And here you get minus 2.38c. They don't match. That is bad. Right? Because momentum conservation is like the fundamental principle of all of physics. How could it possibly, we can't give up momentum conservation. But classical momentum, therefore, classical momentum, which in our notation we would call mu, because remember u is the speed of a particle, is not conserved. Not conserved in special relativity. And special relativity is reality. So classical momentum is simply not conserved. Okay? At low speeds, it's a very good approximation that it is conserved, which is why we think of it as conserved. Relativistic momentum is conserved. So we need a formula for the relativistic momentum. So we're not going to derive it or prove it, we just give it to you in this case. So it is that P, I'm going to do a vector sign just since we're being formal to get started here, is gamma u mu. So normally we're in 1D, we're not writing vector notation, but just since this is our definition, I feel like I should write it as a vector to remind you it is a vector. Okay. So momentum of a mass m moving at u has this momentum, and really the only difference from classical is it has this gamma on it. Okay. That gamma has the same definition that we used before, but here it's u, it's not v. So it doesn't refer to the motion of a frame relative to another frame at v. It also shows up just describing the motion of a mass. Okay, but I'll go ahead and write it down just to make sure you know. Gamma is the square root of 1 over 1 minus u squared over c squared. So sometimes you'll see gamma u, sometimes you'll see gamma v, you'll see mixtures, etc. Okay, so we're not proving it, just
trust me.
So now we're going to move forward and see what that does to physics. So now we want to think about momentum conservation in different frames, purely relativistically. So let's apply the special relativity or the relativistic velocity transform to the relativistic momentum. So just like before, we could set up a little momentum conservation problem. We could show that it's conserved. We could show that the relativistic momentum is conserved. I'm just telling you that it is. And then we could transform the velocities to a new frame and then see if the difference is just a constant and if the momentum conservation will hold in different frames. That's what we want to happen. So what we're going to do is check and see if that happens. If you do it in detail, it takes a while. I did it. It was just a couple of pages. The book leaves it as an exercise for the homework. So see problems 267 and 268 in the back of the chapter. I think they give you a little bit of a hint of how to go about it. But what we're going to do here is look at the answer. So it's sort of like we looked at the other one in detail. This one we're going to look at in a little less detail. We're not going to derive it. We'll just talk about what it looks like. But remember, here's the idea: is we just have, a couple of masses going at each other. We have an initial, we have a final, same thing, they balance off. Momentum is the same before and after, and it has to be the same, it has to be constant in all frames. So we're going to look at this in a frame S, and then in a frame S prime. So let's see, what is the total momentum in the prime frame related to the original sort of lab frame? So here's the answer you get if you go through that whole thing. You get gamma V P total in the non-prime, in the original frame, in the lab frame. So we'll call this the lab frame. This is the moving frame. Right? So what we want to do is just see how do they relate. If we know that this one is conserved, will this one be conserved? That's what we're thinking about. Okay. So let's see. What do you get? You get gamma V times the original. That's good. Minus V. Remember, V is a standard relative velocity between the frames. V, gamma V, again, times the sum over all the particles of gamma U I M I. All right. So this is kind of like what we found before with classical momentum. Right? We said that in the prime frame, it's the original frame plus some term that looked like MV based on the transformation. Now we have the more complicated transformation, more complicated momentum, so the thing looks more complicated. Well, let's decide if it's going to work. Okay, so we know in the lab frame, let's say it does conserve momentum before and after have the same total momentum. What we need then is for all these other things to just be constants and not to affect the fact that if we're just applying constants, then if this one is conserved before and after, this will be the same and conserved before and after. All right. So let's look. What do we have? Or are they constants? So if we look at that's gamma V, that's V, and that's gamma V, and those are all constant before and after a collision. Because all they depend on is the relative speed of the two frames. They don't care about the details of the collision or the speeds of any particular mass or anything like that. Those are good. The question is, what about this? What is that? What they're saying is, what this result tells us is that if you want to see how the total momentum changes between two frames, you got this part in here. It's the sum of each mass times the gamma of its own u. Okay, we did this classically. This was just the sum of each mass times v. And the mass is constant, and v, the relative speed of the frames was constant. Everything was fine. But now it has a u in it. That's bad. Okay. That has to do with the velocities of the individual particles before and after. So you're not sure that that's going to stay constant, right? There's no reason this would probably stay constant. If the mass is constant, why would the gamma be the same before and after when they all have different u's? It could happen, but it doesn't seem like you're sure that it's going to be constant, like if that were a v or a gamma v. So that's bad. So you would think the answer might be, oh, well, maybe momentum just isn't conserved in relativity. Physicists have a little trouble with that. Okay, momentum has to be conserved. There's lots of reasons, symmetry or something, right? So, oh, if we insist, here we go. So, if we insist momentum is conserved, which we do, gamma u times m for every particle must also be conserved. That would be the case, right? So this, whatever this is, has to be constant before and after the collision. So it has to be constant. So what is it? What else is conserved? Right? Energy is conserved. Oh my God, this must represent the energy. So this is related to the famous E equals mc squared, right? If you just multiply it by c squared, it becomes an energy, right? This is unitless. So just multiply it by c squared. So multiply and then you get E equals gamma u mc squared. So that's the energy for mass m going at speed or velocity, whatever, u. Okay, so u is in there. U is in the gamma. So there's a gamma factor, a unitless thing, 1 over the square root of 1 minus u squared over c squared. So that's the relativistic part. That's just the mass and the speed of light. Now, the impact of this is probably bigger than you think right at first. Okay, you could say, let's just tell me energy and mass are related somehow. But there's one word I left out here that's critical for the big idea of this and why it was revolutionary. And that is, it's not just these things, I could already calculate the kinetic energy, 1/2 mv squared. But this isn't the kinetic energy. We've put nothing in this to tell you that it's something about kinetic energy. Okay, well, now I know the gravitational potential energy, mgh. And if it's electrostatic, there's also some electrostatic potential. The point is, when you think about energy, there's a lot of kinds of energy. Then you go in the nucleus, and there's all the nuclear interactions. They have energy. So there's usually this big list of energy terms, potentials, and kinetic, and you add them all up in thermal, and they're hard to keep up with. Right? But the point is, simply thinking about relative frames of motion and the requirement that every frame, the physics works the same in every frame, and that the speed of light is the same in every frame, leads to this. It's not just the energy, it's the total energy. Okay? Without knowing any details about the little micro mechanisms that are responsible for each kind of energy, it just works out that you know the total energy by mc squared. That's why it's revolutionary. It's a way to get all that microscopic energetic information without knowing any details about it, just from something that simple. Okay, that's the big deal. So I think what I wrote here is a way to get total energy with no internal details. And there was absolutely no idea that there would be a way to do this before relativity. Energy with no internal details. And next, we're going to go through what all you can learn from this and how you use it. Okay, so what we have is a particle or any mass m at speed or velocity u has total energy E total equals gamma u, so 1 over the square root of 1 minus u squared over c squared, mc squared. Okay. So many implications of this. We're going to talk about a lot of them. We're going to show you how to use it for problems. But first, let's break it down a little bit into the different kinds of energies. What's amazing about it is it's everything. All the little microscopic potential energies, all the interactions. But let's break it into a few common things that we worry about. So let's break into internal and kinetic at least, because that's still a special divide. Kinetic energy is special and different from internal energy. So we start by saying, well, E total, as we know, is the internal energy plus KE. That's what the book uses. So we'll write it KE. So first we can start by saying, what if there was no KE? Right? What if there was no kinetic? What if the particle is at rest? Well, then that means it's not moving. U is 0. So if we're in the rest frame of the particle, say U is 0. If U is 0, what is gamma U? If U is 0, gamma U is 1. 1 with the square root of 1 minus 0 is that. And therefore, the kinetic energy also, if something is not moving, kinetic energy is 0. So if you took all this and said, what's going on here? Well, U is just 1. Right? So for any particle, if you want to know its energy when it's not moving, it's just sitting there, and all the little internal energy going on with it, whatever mechanism it is, it's just mc squared. Right? So that's the famous E equals mc squared. Without the gamma on it, it means for something not moving, essentially. This, also important, is the total energy. What if we wanted the kinetic energy? Well, then you just flip this one around, and you say the kinetic energy is the total energy minus the internal energy. Right? So then you can sort of abbreviate it like this. It becomes gamma minus 1 mc squared. Gamma u minus 1 mc squared. And if you ever wanted it, you could just calculate this and calculate this and subtract them and whatever. But the point is, an easy way to remember it is a simple formula you'll use a lot is gamma minus 1 mc squared. Okay, so for any particle moving around, this is what's happening. Okay, so for a lot of problems, I like to think of it in a plot kind of like this. If we think about u here and gamma u here, then you know if you go all the way to 0, if the speed goes to 0, then gamma goes to 1, right? But then as you speed up, gamma kind of does that, it goes up. As you approach c, it goes to infinity. So I think of this as the internal energy down here and the kinetic energy up here. There's sort of a constant internal energy affiliated with the particle and how much mass it has and everything. And then it kind of grows with kinetic energy. And you can see that here, right? The mc squared is just mc squared when this is 1 and when it's not moving. And as it moves, this takes off and blows up, okay? So one thing, and then now I do want to point out though that the internal energy, if the internal energy changes, the mass will change even without worrying about kinetic energy. So we'll get to that in a minute. But for now, let's just pretend we have a simple situation. Particles are at rest, they have some internal energy, they begin to move kinetic. But one thing we want to point out is we will not define a relativistic mass. It looks tempting to say, oh, well, this is the rest mass, and gamma m is the relativistic mass. And therefore, we're calling it m naught or something like that. So we don't really do that, okay? We just define the mass, or we just define the rest mass. Okay, we're not going to worry about the concept of a relative, the idea that as it speeds up, it gets more massive. We don't really think of it that way. Our m that we'll keep writing is the rest mass. And also the mass, I like to add when it's alone, okay? Because in principle, that M can change if you have like two protons close together and you push them together and you create more electrostatic energy. Their mass actually goes up. Or if you get something hotter, its mass does go up. So the M's we define, like the mass of the proton, 0.938 GeV per c squared. That's just an isolated, lonely proton with nothing special happening to it. Okay, and also if you want to read about why, page 38. They talk about it and how Einstein himself said, don't think in terms of relativistic mass. I think some older books do that and it gets confusing. So now we've seen that special relativity, looking at momentum conservation, leads us to new things about energy. And I just want to comment on one about the internal energy equal mc squared. Okay, so we talked about the total had the gamma on there, but the gamma has to do with it might be moving and kinetic. So if you ignore kinetic, if you say it's not moving, that's all it is the internal energy equals mc squared. So next thing I'm going to tell you isn't super important for most problems, but it is the idea that what if you have, so say you have a particle here, and it's alone in the universe, okay? It has some mass, and it has some internal energy. If it's just a hydrogen nucleus, it was just well, something more common, a carbon nucleus, then a lot of that internal energy is all the nuclear physics happening, all the strong interactions in there are setting that mass. But there are also more large-scale, real-world things that you can do that can change the internal energy. Not the kinetic, but the internal energy. And therefore, they literally do change the mass. Okay? So the problem I want to think about is two protons. Okay? So two protons, 1 kilometer apart. All right, so proton here, way over here, proton here. And they each have the standard proton mass, 1.67 times 10 to the minus 27 kilograms. Proton, 1.67, 7 times 10 to the minus 27 kilograms each, okay? And we know, of course, they have a positive charge. So what we're going to do is push them to where they're very close. As you imagine, this would take a lot of work to where they're 10 to the minus 14 meters apart. So sort of is that a nuclear scale? Yeah, like the scale of a nucleus, on opposite sides of a nucleus. And let's just think about how much energy it would take to do that and how much internal energy we're adding. Okay, so first let's do isolated before we do that. I'm doing this out of order. So. Okay, so isolated, let's just do a quick mc squared, right? So the E internal for each one is going to be that 1.67 times 10 to the minus 27 kilograms times 3 times 10 to the 8 meters per second squared. Right, so you just do this standard calculation. We're going to do it in joules, and we're going to get, and there's two of them. Right, they're a kilometer apart, but there's two of them. Their total internal energy is 30 times 10 to the minus I have to write bigger, 11 joules. Okay, so in this state, a kilometer apart, that's the energy. Now, let's push them to be really close. And what we're going to do is that's going to add internal energy to the system. So increase E internal by, and it's just going to be, we're going to do a quick electrostatic calculation. Right? The delta big U, for electrostatic energy, ELEC, not speed. It's just KQQ over R, right? So go back to electrostatics, QQ over R. So we could do it for really close minus a kilometer apart. The kilometer apart will be essentially 0. So let's just plug that in. So the U, the electrostatic potential, or the electrostatic energy we're adding is K, 9 times 10 to the 9, QQ 1.6 times 10 to the minus 16 coulombs squared, because there's two of them, One creates the field and the other you push against the field, and over r, 10 to the minus 14 meters. All right. So the energy that creates is 14 times 10 to the minus 15 joules. Okay. Okay. So then we can say that the internal energy equals this base amount we had, 30 times 10 to the minus 11 joules. But now we've added 14 times 10 to the minus 15 joules. Okay. So since the internal energy is proportional to the mass, this increased the proton mass. When we push them together, they literally were getting heavier. Nothing to do with kinetic energy. We're doing it slowly, and they're at rest when they're far apart. They're at rest when they're close together. But we're literally increasing the mass of the protons. They are becoming heavier, but only by increased proton mass by 1 part in 10 to the 4, right? Because 10 to the minus 15, 10 to the minus 11. So what the big revolution was is that mass is simply a measure of energy. The more energy you have, the bigger the mass gets in terms of internal energy. Okay? So it's very weird to think about. You think of the mass of the proton as a fundamental constant of the universe, and it is. It's just an isolated proton, it is. But you can actually change its mass. You can literally, if you have these two closer together, if you want to get them to a certain acceleration, you will have to push them harder by 1 point in 10 to the 4. So if you want to read there's a certain page in the book that sort of discusses this and assures you this is what's really happening, even if you have a balloon and it has a certain mass and you heat the balloon, it weighs more. Right? And it talks about how you can think of it that way. Yeah, the sort of detailed discussion is page 38. Look at 38 and it kind of walks you through this wild idea. Now, a lot of our homework problems are more about the kinetic energy and when something starts moving and it has momentum, and we're talking about collisions. But this very fundamental idea, I want to make sure you understand, this is all very real.